the rest of this class. So last week we were talking about, as I said, centers of measurement. We have the mean, which most people call average. Average is a loaded term, both from a mathematical and a sociological standpoint. So statisticians prefer mean to very specifically refer to the arithmetic mean, the sum of all data points divided by the number of data points. So remember that the mean is what we call a non-resistant measure of center, because it can be greatly influenced by outliers. Okay. How do we recognize outliers? We'll get to that in a moment. We have various means of looking at data that allow us to do that. Because we need to have a very defined measure of what that term means. The tendency in accumulating data, whether it be business data or scientific data or medical data or anything like that, the tendency is to look at a data point and throw it out because it doesn't fit your personal criteria. The statisticians want to have a reason to place that outside the data set. So we have then we have the median, which is basically the center point of your data set. So you take your data set, you put it in order, and you go to the middle. If it's an uneven number of data points, that's going to be right on one of the data points. Your median is the value in the middle. If it's an even number of data points, it's going to be between two, and we take the mean of those two by simply dividing them, adding them together and dividing by 2. That gives us the mean of an even numbered data set, or the median rather. Okay, we have mode. What is your most common value? We saw that in the satellite data. 157 for one country, and then it dropped off to 18 and 14, and then a whole string of ones. The most common data point is 1. So is that 157 an outlier? Well, it certainly sounds like it to me. Okay? Sounds like it to me. So we would look at that and say, well, then this country, we just exclude this from our analysis for some purposes. But you don't throw any data. A statistician will not allow you to throw data completely out. It will allow you to not mark it as being an outlier or not being likely or whatever, but you don't throw it out because it's still data. You may question whether the data have been correctly determined. That's the experimenter or the study director's job, is to determine if that's reasonable. Let me give you an example. Last year, Larimer County went through and revalued all property, all residential property. And the property value on our house seemed kind of high. Now, I know why they do that. They want the tax revenue. But that's not an excuse to artificially make it high. So I went in and I said, okay, what the heck's going on here? And I looked at what they used, and you can get all this information off the county site, by the way, what they used as comparable sales in the neighborhood. Well, most of us think of our neighborhood as a fairly compact, small area, because we all know that you can have, in our society, you can have a neighborhood of houses that were built in the 50s, and then a neighborhood of houses right next door, right across the street, houses that were built in the 2000s. And you would expect the houses built in the 2000s to be worth a lot more. So how you define neighborhood skews your data. Well, I was looking through and I found one of their comps was a property that theoretically, I say theoretically because I wonder if this is an incorrect number, or if it had been rezoned for commercial, which is another possibility. Sold for 3 times what anything else in that area sold for. So instead of like 300,000, it was like 1.1 million. And I said, that data point right there is screwing everybody up all through. You can't do that. Good morning. You can't do that. So you do, and I never got an answer to the question, was that a real price? You know, was it a data entry error? Or was it not residential, but had been converted to commercial property? In which case, yeah, it's going to go higher, but that shouldn't affect my house value, considering that I'm a mile away from it. So, you know, so you have to look at how the data are, you know, you look at an outlier and ask if it's real. And a lot of times it is. You know, like that satellite number. That's probably a real number. Actually, it's probably an old number. There's a lot more up there now. And if Elon Musk has his way, he's going to throw up 20,000 satellites to make internet available worldwide for everyone. A laudable goal. But then, does that mean the United States now suddenly has 21,000 satellites in orbit? Could be. Depends on how you do your data, right? To me, that's not a US satellite. That's an Elon Musk satellite. But nonetheless, you know, there we go. It depends on how you define your data. So our measures of center, now we've talked about mode, median, and mean. Others that we've talked about are looking at how the data are grouped. And one of the ways we look at skewing of the data is through, you know, we can graph it out, you know, where we have our data skewed one way, we'll have a tail on it way out. We've seen that with the pulse rate data in women. There were 2 data points that were pretty far out, pretty far downstream compared to the bulk of the data at the beginning. That's a skewed data plot. And we can see that with histograms. It's not quite so obvious with frequency plots. It's much more obvious if we use the frequency polygon, right? Because it's basically one of those kinds of curves. It's just that it has angles and vertices. But another way of looking at it is the box plot. Remember, we talked about that. We divide the data. I was explaining to Brandy and Richard before you came in, April. One of the problems was a data set, looked like about 20 numbers. And it was, the interest was, you know, how do we calculate a percentile? But I'll come back to that in a moment. The data need to be lined out. You need to have your data in order. The box plot actually comes from putting the data in numerical order. It doesn't matter to me if you go top down or bottom up, but convention is you start with the lowest number on the left and go to the highest number on the right. And then just group it. Count up the number of data points, mark it off into quarters. And we're only talking about not the values of the data. We're talking about the points, the number of points of data we have. So we construct the box plot, and we have a minimum, we have a maximum. We have a center point of the data, which is really about the median of the data, right? Morning, Nate. We have the center point of the data, and then we have the beginning of the second quartile. In other words, you mark off the data points into quarters by numbers of data points. So if we've got 20 data points, the first quarter is going to be the first 5 numbers. The second quarter is going to be numbers 6 through 10. The third quarter will be 11 through 15, and the last quarter will be 16 through 20. Just mark it off with a box. The boxes don't have to be the same size, same shape. Okay, they're really usually rectangles, so they will vary. And looking at those data points, that's how we look. That's a good way to look at how to determine if certain data points are outliers. And remember what we said was that any data point that was 1.5 times what we call the interquartile value, meaning the value of data that is at the beginning of Q2 and at the end of Q3, the third quartile. That range, and there's where we go to the absolute values. That range, and we calculate that. So if our data is such that that interquartile range is, say, 5, and we are looking at the value of the data at the beginning, the value at the end, and calculating what that span of data is. If the distance from the top of Q3 to a data point is more than 1.5 times that interquartile range, we consider it an outlier. We don't ignore it, right? We don't ignore it. We list the data, but we also note that it is considered an outlier for whatever purposes we have. That doesn't mean the data are wrong. It just means that it's an unusual value. And it's how we determine that something is of inherently a low probability. Usually speaking, we're not going to have lots and lots of data out there. Otherwise, it will drag everything else up. So it usually is a few data points. Other ways we see this are when you see a line of data and you see a bunch of data points. And you've got one data point way the heck up here on a line where most of the points would be expected to be, say, here. We've got one way up there. The temptation is to say, oh, that's an outlier, and ignore it. But you can't just ignore it without reason. So you have to go through a different set of analyses. And that's one way of doing it, using the box plot and the interquartile range. Remember, statistics is about data. Data that are numerical are inherently easier to work with in this respect. Data that are qualitative. Let's just go back to the old question about what's your favorite color. You know, most people are going to pick something off the rainbow. Red, orange, yellow, blue, green, violet, maybe. But every now and again, you're going to get somebody who's going to say chartreuse. Okay. Is that an outlier? It's a little, yeah, probably. I mean, if you look again, if you've surveyed 10 people, probably no, because you've already gotten a big range for a small number. If you've surveyed 10,000 people, then potentially this is an unusual result. But it's a little harder to work with, because what's the interquartile range of colors? So there it's a matter of looking at the likelihood of the next person telling you chartreuse. If you've done 10,000 people and one person has said that, then the chances are about 10,000 to 1 against you that the next person will say chartreuse. In which case you can probably say this is not a likely outcome. Is it possible? Yes. If you can calculate a probability, it can happen. The only things that can't happen are things that are physically impossible, like me jumping over the building. Okay? And remember, the whole idea with statistics just for the sake of statistics is a nice little mathematical exercise. But if you can't relate it to something, most people are going to look at you and say, so what? And properly. I like math. I like to play with math. I like math games. But I also recognize that I may not be in the mainstream on that. And so but the real issue is that one of the reasons I don't have a degree in math is that I made the mistake of asking the head of our math department when I was an undergraduate taking a class in what we call group theory about the practical application of that. Because at that time, I was also studying, my degrees are in chemistry. So at that time, I was taking a chemistry class in which we were using group theory to predict chemical reactions. So I asked him about practical application. And he, in front of an entire class, just really ripped my head off and shoved it out the window. And I said, you're an idiot. And that was the end of my math career. But the issue was, I want to know what use it is. Math for math's sake is okay, but that's statistics for statistics' sake is, interesting, but who cares? I don't care what the likelihood is of someone in New Jersey picking a red car. That's totally irrelevant to me. But I do care about the statistical probability of some moron on the road running me off as I'm driving in Colorado, where we have a lot of morons on the road. Not just Colorado. But so I do, but math should have a practical application. What is the practical application? Well, with statistics, the practical applications are the prediction of and the ability to make business decisions in the business side, the ability to make business decisions based on likely outcomes of those decisions. Now, this requires that we not only understand what the decision is, but understand the data that we need to make that decision. Probably. Yeah. Mm-hmm. Right. Right. Yeah. And in doing so, you need to take into account seasonal differences, right? Right. Right. Mm-hmm. Right. Yeah. And we're going to get to something in this chapter that allows us to, these are conditional probabilities. These are probabilities that change based on changed information. Okay. So, that's it. I mean, it depends again on if you're looking at the hotel as a whole or the hotel as this is what we are able to actually rent out for a night. And again, what that tells you, if you've got 100% of your available rooms being rented out and you're having to turn people away, that gives you an incentive to get that second floor finished, right? But that doesn't mean that when you open up that second floor, those other 30 rooms are immediately going to be filled. Now you have a different data set, right? Right. Mm-hmm. Yeah, costs money. Yeah. Well, yeah. Well, someone, theoretically, someone should have been looking back over the data to see how often that room was rented. If it's not rented very often because it's expensive, then one does have to question whether that's a good use of one's space, because it still costs you money to maintain that space. And jacuzzis are horribly expensive. That would seem to make it worthwhile. There's a different perspective. That's what you want to do. The issue, but again, now you're seeing how how a business decision needs to have all the information. And what statistics does is allow us to sort of structure what information is needed. So I'm sitting here listening to you and thinking, yeah, he's angry because only 50% of his rooms are rented, but 50% of them aren't available. Therefore, they really don't count. And you have to consider that. Now, at the corporate level, that's usually a method they use for beating on managers. Oh, you only have 50% occupancy. They don't care that they have authorized, because you as a manager, you don't just get to do it on your own. They've authorized, but they use it as a means of pushing. But again, as I say, okay, you're going to open up another 30 rooms. You're going to close down 10. So now you've gone from 30 to 50 rooms. Ah, okay. Okay. So you have 75 rooms. So you're going to go now, theoretically, at this point, you're going to be going down to about 65 rooms. One of the things you look at is what is the average occupancy, and setting aside, a lot of your business is going to come during the week from business travelers. Your weekend work is leisure work mostly. Mm-hmm. Mm. That's too bad. The Irish. Sounds like a wake to me. Mm-hmm. Yeah. I, yeah. I guess Holiday Inn Express must be doing a lot of that because we stayed at a couple when this summer when we drove up to Idaho, and one of them, someplace in Wyoming, that was what was going on. Is the meeting room was full of stuff from Reconstruction. So interesting. Mm-hmm. A little. Yeah. Yeah. Well, again, they're not the ones dealing directly with the customers. So I mean, let's go back. I mean, if we talk about that, I mean, you look at what you're doing, and what you're doing is statistics, and using those statistics to predict the potential for future business, which allows you then to look at your hiring, how many people we need to have working, what our costs of maintenance are going to be. I don't know if you have in-house employees that do your cleaning and daily room maintenance, or if you use an outside contractor. Mm-hmm. Yeah, yeah, well, but being at least partially bilingual is an absolute necessity in that respect. So again, what you've done there is someone made that decision based on the idea that you have all these employees that need to be communicated with. There has to be an intermediary someplace. Hmm. Yeah. Oh, of course not. And that's it. Again, that allows you to determine how many of your housekeepers you need, because you can figure out what is the expected um, output in terms of rooms done. So that's all about statistics. It's all about gathering data and what you do with it. Does that mean your next person hired in is going to do 15 rooms? No. But that does mean that if you bring in more people, you might expect roughly that number of rooms to be taken care of. So when you open up this next floor and get 30 more rooms or so, you know you're going to need more help. And so either you schedule people into more shifts or you hire new people. So again, you've gotten statistics. If we go over to the IT field, there's lots of places that statistics are used in a multiplicity of areas. You know, the clock speed that we have in our processors, that's a statistical number. Not every processor is going to exactly have the same clock speed. It should be very close if your quality assurance is good. And that's how they go through and do the quality assurance. You look at the percentage of these things that don't meet the requirements, right? You test them. You don't test every one. You make sure everyone's working. I mean, that's part of the final QA of any manufacturing run in something like that. Somehow or another, you have a quick test that says, yeah, this is working. There's not a broken, whatever, someplace in it. But does that mean that everyone has exactly the same clock speed? It's a range. It's a range. And you have some acceptable percentage of these in a sample is going to be in that range. And you do this by sampling. Theoretically, could you test every processor produced? Yeah, you could, but the cost of such an endeavor and the time required for such an endeavor are not going to be invested by a manufacturer. So we use statistical methods. It's like the computer question in one of the homeworks. We use a statistical measure of the functionality, and we take a sampling and we test. And there's all sorts of protocols for determining how to pick that sample, but they all really boil down to making certain that somehow or another you have a good representative sample. It's been randomly chosen. Hopefully, every single computer produced has the same chance of being randomly selected for testing. And then you use those data to determine what, I'm going to call it failure rate, because I'm not sure what the proper term would be in IT, but what failure rate you might expect, how many computers you might expect to be brought back to the store because this thing doesn't work. And you want that to be as small a number as possible. So you usually use these statistics to see where you're having troubles in your manufacturing process. I see. Okay. And of course, in medicine, we use statistics all the time. That's how we prove. Come on in. Time for break. Is it? Oh, it is time for break. I'm sorry. Let's take a break. Let's take a break. Okay. So, in the medical field, it's all about statistics. And they're applied throughout medicine. From insurance, which is really based on the likelihood, the probability of a payout. Insurance companies are not in there to make us better, they're in there to make money. So insurance rates are set up on statistical guidelines based on the likelihood of paying out money and how much that is. The rules for insurance can be played with, but that's the basis of theoretical basis for establishing a price. The value of medical treatment is a statistical issue. Not everyone responds to a drug. Not in clinical trials, and certainly not in real life. And so there are a number of different statistics we use when we're looking at drugs. One being the statistical likelihood of the drug having a beneficial effect on the patient. The second is a statistical likelihood of the drug actually doing harm to the patient. hopefully the statistical likelihood of the drug doing harm is significantly under that of doing good. In fact, if it is not, then the drug is not likely to be allowed to be used by the physicians, or there will be warnings placed on the use of that drug. But it's all based on statistics. So what we do is we look at the percentage of people taking the drug that actually show a benefit versus the percentage that do not show a benefit. Hopefully that is going to be a significant difference. Okay. So statistics, so the use of statistics really in looking at probability. Remember, statistics is the collection and analysis of data. Probability is the use of those data to predict future outcomes. Okay. The probability of something in the past is either 0 or 100%. Yeah, it's already happened or not happened, right? So we use, but retrospective data allows us then to calculate the probability of certain things happening in the future. And we do that a lot. Remember, there are retrospective studies. There are prospective studies, but prospective studies are something that is ongoing. At any one time, all the data in the past is now retrospective. The data we collect in the future will be prospective. What we are trying to determine with prospective studies is, over time, we're trying to learn about large populations of people. As I said, in the medical field, one of the largest prospective studies that we have is the Framingham Heart Study. And this is a study that's been going on for decades, I think since the 60s at this point. So we're approaching 6 decades of data. Many of the original participants in that study, of course, are no longer with us. So what we've done is tried to use their health outcomes, and by the way, the ultimate outcome of anyone is going to be death anyway. So what we try, well, it's a death sentence. You know, the greatest cause of, the largest cause of death is birth, right? That's right. We all die. Nobody lives forever. Some live longer than others. It's the only thing we can say. But we do use the data that we accumulate, on cause of death to predict the likelihood of a large population of what percentage of people will have certain health issues. Okay? So prospective studies are commonly used to determine this. But the purpose of this is to develop a statistical picture allowing us to establish predictions of future events. There are studies that are static. Okay. The census is something that is essentially a static study. We're looking at a period of time, a point in time. This is a cross-sectional study. We're looking at the population at this specific time period, usually the summer months of a year ending in 0. Okay. We use it for a purpose. It has a purpose. It allows us now to reapportion Congress. But the picture is a static picture. It does not, we can look at past census data and maybe make projections as to what the demographic distribution in the country will look like in the future. But what we can't take into account is the vagaries of human behavior. The original purpose of the census was to, as I say, to apportion, set up the representative portion of our government in Congress, the House of Representatives. And that is a fixed number. Congress can occasionally and does occasionally increase that number, but it's a fixed number. At this point, it's 435 members. That's who we have in Congress. So we have, so what we do is basically we take the population of the country at the census, divide that by 435, and we use that to say, okay, for every whatever number of people you have in your district. This is going to be the size of a district. And we look at the population of states and see how many times this district size would fit into that state's population, and that's how they get more or fewer representatives. Now, it gets a little bit skewed because, of course, there's a minimum of one. So that every state has some representation in Congress. But there's a minimum of one representative. So it does skew it skews the data a little bit. But nonetheless, that's how we use it. But that's a point in time. Over a period of census, we can say, okay, this ethnic group is increasing, or this political party is increasing or decreasing. And we use it on a state-by-state basis. And it's how we determine what our population distribution is and how we make plans. We also use it for looking at the needs for, for public assistance. So all of this goes into these databases, and we start looking at and analyzing the data for specific purposes. In my sort of, I guess, task-oriented mind, we should never collect data just to collect data. There has to be a purpose to it. Maybe I don't know what that purpose is, and I will say that sometimes I look at the data and say, "What in the world do you want to know this for?" But I am not privy to what the purposes are. But for the most part, and I think most statisticians would agree, you don't just accumulate data to accumulate data. Now, there are people who do that. We have a society where, we have people who are accumulating data on us for whatever their purposes are. I'm thinking specifically of the multitude of reports about the National Security Agency monitoring all of our emails and phone calls and so forth. But they have a purpose for that. Whether or not you agree with that purpose is irrelevant. They have a purpose. Well, that's not the way they look at it. Okay? I personally find it an invasion of my privacy. And I hope they're bored to tears by what they learn about me. No, they're not. They have algorithms that pop up information that makes them want to look more closely. As I said, if they were looking at my email and telephone communications, I think they'd be bored to tears, which is just fine with me. But nonetheless, that's how they capture information. We've seen this with with what's going on in Washington now with the Robert Mueller probe. A lot of the data has actually come out of monitoring communications between these people they've indicted and foreign governments, and that's how they've done this. So they're, as I said, you may not agree with their reasons, but they have reasons. But most people don't just accumulate data. There are some people that are just data beans, and they will accumulate lots and lots of data. What they do with it is, who knows? That's not our business. But there has to be a reason for accumulating data. But let's take a look at probability. And we're looking at our textbook at the moment. I want to just a second here. Okay, let's go back here, and we're going to share screen. All right, so some basic concepts. An event is any collection of results or outcomes of a procedure, okay? Again, let's go back to the reason we have definitions is that so everybody knows what we're talking about. Event means a lot of things to a lot of people, okay? So in statistics, we put some and in all sciences, we put very specific definitions on our terms, or we try to. A simple event is an event that can't be broken down into simpler components. Okay, an example of what a simple event might be is an experiment that says, okay, I've held that lead ball on the roof and dropped it. Okay, that's a simple event. It can't be broken down into components. Once you let it go, it happens. A non-simple event, something can be broken down into components, might be trying to analyze an automobile accident. For the most part, they're not something that just occur, you know, because of one single event. It can. Your accident might be that you slid off the road in a snowstorm because you were going too fast. But there's two components. You're exceeding the safe driving speed for that road, and the consequence was that you slid off the road. A multiple car accident may have a number of components and a number of different people. I was watching a video recently of a 70-car pileup on I-35 in Iowa in a snowstorm. And I was watching this Department of Transportation, Iowa Department of Transportation video cam of that event. And I was watching people do the stupidest things. I mean, people roaring up to an accident, to a pile of cars at high speed and then hitting somebody else. You know, just really stupid. But the components of this were a very complex set of components. Some people took evasive action and their cars went off the side of the road. You know, some people took evasive action and managed to keep their car on the shoulder. And then I watched a couple of them get hit from behind. So multiple components. So these are not simple events. These are complicated events. Sample space, all possible simple events. Okay, so that was a sample space, that Iowa accident. Our notation. Okay. The notation P, usually in italics, indicates a probability. Okay. And a specific event is given a number or given another letter, an A, a B, a C, or whatever. And the probability of A occurring is represented by P parenthesis A close parenthesis. We read that as the probability of A, or P of A, is how that is worded. Basic procedure, basic rules for a probability. If we want to know the probability of A, if we want to know P of A, we look at the number of outcomes, the number of times A occurred out of the total number of times that the procedure was repeated. So again, if we look at if we didn't know intuitively about that die, that single die, and we wanted to know what's the probability of rolling a 1, we'd roll the dice a number of times, or roll the die a number of times. And that number of times would have to be sufficient to give us a good picture. Probabilities can be influenced by a couple of different things. One is the number of repetitions of the experiment that you do. Okay. If you do smaller number of experiments, if we rolled a die 6 times and 2 times it came up 1, we might be tempted to say, okay, the probability of a 1 was 2 out of 6, or 1/3. Intuitively, we already know that it has to be 1 out of 6, as long as the die is on. But we know intuitively. So that's an example of, we look at that and we say, okay, we haven't done enough experiments. Now, can we do enough experiments? Well, rolling a die, it's, you can. I mean, you might spend an afternoon and roll it 10,000 times. Let's make it easy, 6,000 times. And get a 1 about 1,000 times. But again, about. Probabilities approach the theoretical maximum. They don't necessarily hit it exactly. Okay. The maximum, the probability over an infinite number of rolls of one die would be 1/6 of the time, exactly 1/6 of the time. You would get a 1. You'd also get a 2, 3, 4, 5, and 6, 1/6 of the time, in an infinite number of rolls. If we were to roll the die 6,000 times, we might get 988 ones. And then we might get a few more of something else. That is a theoretical possibility. It is also very unlikely. Okay, that's an example of something that, the fact that you did not get a 1 after rolling the die 6,000 times is very, very small. That's an intuitive answer, but you can actually calculate what that might be. And it's very, very, it's a number that is ridiculously small. However, as I said, if you can calculate a probability, it can occur. It's just that you might have to do this far too many times in order. But again, in an infinite number of rolls, and of course, infinite means that is kind of a meaningless term, but I mean, these theoretical probabilities are going to hold as long as everything else is held constant. We can influence probability. I mean, people do it with dice all the time. They're loaded dice. Loaded dice have been around as long as we've had dice around. But as long as the dice are honest, we'd expect that, okay? So P of A is the number of times A has occurred over divided by the number of repeats of the procedure. And again, we assume that the procedure is repeated exactly the same every time. Yeah, that would be, if you rolled it 1,000 times, that would be the number on the bottom. That would be the denominator. At the top, you would just have the cumulative number of times that you got a 1. Okay. And what happens specifically with things like dice, of course, we can do these things theoretically, but from a practical standpoint, you roll the dice, you record the number. You roll the dice, you record. So you record the results. Now, is it possible to measure all potential outcomes? No. I'll go back to clinical trials. one of the things about clinical trials is that we know that drugs have side effects. Some of those side effects are serious, and some of those side effects are potentially lethal. Many years ago, there was a drug developed as an anti-infective drug. Chloramphenicol was the name of the drug. Chloramphenicol was seen as a miracle drug. I mean, it really wiped out some infections that were difficult to treat. And so immediately after it was marketed, this was marketed in the 50s by the Parke-Davis Company, which is now part of Pfizer, I think. But the Parke-Davis Company invented this, marketed it, and it was an immediate big sell. Millions of people started using it. And all of a sudden, we started seeing something that wasn't seen in the clinical trials. We saw a certain level, about 1 in 15,000 patients, developed something called aplastic anemia, which is a deadly form of anemia. It happens when you destroy the erythrocyte producing, the red blood cell producing stem cells, make it impossible. So now, 1 in about 15,000. Now, if you treat millions of people, you can see that number. But in clinical trials, we don't treat millions of people. In clinical trial, we treat thousands of people, not millions. Sometimes a clinical trial can go up to 10,000 people. But if it's 1 in 15,000 chance of seeing this, the chances of us seeing a 1 in 15,000 event, even in 10,000 patients, isn't that great. Okay, it's a lot better than seeing. It's a lot better than say in 1 in 1,000. And I'm sure that given when chloramphenicol was developed, there were probably not more than 1,000 patients in the entire clinical trial program. It took widespread use, and then we started seeing the statistical emergence of this problem. So in reality, we wouldn't even expect, if we treated 15,000 people in a row, we wouldn't necessarily expect at that point to see one of these events. Okay? In order to have a likelihood of seeing that event, we'd have to treat a lot more. And so could we have seen, if we had treated 15,000 patients in the clinical trials, could we have seen one case? Yeah, we could have. The problem is, of course, that we have, what we need to do is relate it to the drug. Again, statistically, people develop diseases. I mean, you've all seen drug commercials on TV. And what they give you, the warnings. The warnings start with, mild headache, nausea, blah, blah, go all the way up to sudden death. Well, if you hear that last phrase, sudden death, you think, well, I don't want to take that drug. And the problem is people die of causes unrelated to drugs. But we have to report those events in our clinical trials because we don't know if it's related. Especially low probability events, we don't know if they're related. And an event like sudden death, I mean, people do literally, there's one phrase I always told my daughters never to say, and that's drop dead. Because people do.
Yeah, and just
No.
they die
Yeah. How are you going to feel if the next day you find out they dropped dead? And literally they do. We had it happen to a friend. Healthy individual who just dropped dead one day.
From what?
Apparently his heart just quit. And there was no evidence of heart disease.
Yeah,
That's a direct cause. Yeah, too much caffeine will send your heart into. Too much caffeine will send your heart into fibrillation, and you could die. That's why they're starting to really look at these energy drinks and say, is there a problem? How do we know this? Statistically, we started seeing it happen. We started seeing it happen. There is a chance, and it depends on the individual. I mean, but it also happens. We've seen it enough. It's sort of like people taking ecstasy, drinking so much water that their brains swell and they die.
They drink too much water.
They drink too much water.
What?
You think water is essential, but water, we think about water being deadly only if we drown in it. No. If we pump too much water into ourselves too quickly, our brains can swell and we can die. That's one of the reasons that ecstasy is so dangerous. You get this false sense of thirst and you can't quench it except by drinking huge amounts of water. And then you die.
And then you die.
So,
Hallelujah.
yeah. So, so we find these things out by the data. And we look at them and say, oh, okay, is this statistically significant? As I said, we know that people simply drop dead. And we know this happens. But is it related to a drug? Our friend who dropped dead took no drugs, was not a smoker, not a drinker. Regular exercise, good diet. His heart simply quit. And that happens. I've had that happen to one fairly close friend and two acquaintances. Just all of a sudden, they're standing there and then they're on the ground and they're gone. So statistically, that happens too. So we need to look and so we have to look at what is the cause. With my friend who died, there was no way to relate it. The other two acquaintances were both heavy smokers and drinkers. So maybe that was related to that. I don't know. But none of them had any clinical evidence of heart disease. So it happens. So we see these things. And so statistically, we ask ourselves, what is the chance of someone dying on a drug? We can't say there's no chance because we can't relate that to completely outside causes, especially in a clinical trial. We can't relate that to solely outside causes. Even if we can go back and say, well, the most likely explanation is not this drug. Okay. So there's lots of reasons that we use. Look at the number of times something occurs, and then divide that by the number of times we proceed the procedure. Now, let's look at like rolling dice. Dice, clearly, there's an equal likelihood, or flipping a coin. There's an equal likelihood of the outcome. When you roll one die, you can have one of 6 results. And they're pretty much, you can look at it and say intuitively, each of those is as likely as each other. So these are the same thing. With flipping a coin, there's the old, usually people will object when I say that flipping a coin, you have 2 possible outcomes. Somebody will say, well, what about the coin landing on its edge? Show me when it's happened. Pardon? Well, start flipping. But really, I mean, show me when it's happened. I mean, that is such a low probability event that it is not, it's so unlikely that it has no effect on the outcome of flipping coins. I've never seen anyone flip a coin onto a hard surface, flat, and have it land on edge. Yeah, it's not gonna. It's just the outcome is so unlikely. So the number is so basically we have the probability of A is again the number of ways that A can have over the number of rolling a die or flipping a coin is a simple event. It's either heads or tails, flipping, and you have an equal chance of having one or the other, or you have, same with the die. We talked about that. So there's lots of ways to calculate that, but but also if we look at that, there's something called subjective probabilities. We can estimate, and we do this a lot, especially all of this. I mean, we can look at it and say, okay, this is a logical constant. We know that a coin can land either heads or tails if it's just flipped up and allowed to land on the surface. We know that a coin can land one way or the other. That really is an intuitive or subjective, meaning we're making a judgment as to what the answer can be. The same with rolling dice, one or two or however many dice that we have. So we have, we understand from the circumstances what that's likely to be. Where those circumstances can't be readily predicted, we need data. We can also, but you'd be surprised at how much of the data can be done subjectively. As I said, if you do this enough times, you're going to approach your theoretical maximum. Flipping a coin, getting heads twice in a row is a likely outcome. 50-50 each time. So it's 50% the first time, and then you have another 50% of heads the second time. So that's 25%. So if you flipped coins and did a lot of repetitions of two rolls, you'd expect, or two flips, you'd expect about 25% of the time to get the same result. Okay. So as I said, if you repeat again and again, you're going to reach a practical result that you've already calculated. As I said, rolling a die 1,000 times, you'd expect, well, let's make it 1,200. I can divide that easily. You'd expect 200 ones. But what if you get 202? That's not yes, the end of the world. It doesn't invalidate the statistical probability. What it does is say that you need more numbers, because this is an intuitive issue. We can predict subjectively what the outcome is. We can't predict subjectively the outcome of complex events, like the likelihood of an accident on the road when you're driving to work. We can't predict that because it's a complex set of events. This can only be done through observation and data collection. Okay. What are the limits? Okay, obviously something that is impossible has a 0% probability. Something that is certain has a probability of 1 or 100%. Okay. Okay. All probabilities, by the way, of all possible outcomes of an action add up to 100%. Okay. So again, if we look at rolling a die, we've got a 1/6 probability of getting a specific answer every time. And and having that, but since there's a 1/6 probability of getting a 1, a 1/6 probability of a 2, etc., it all adds up to 6/6 or 100%. So probabilities can never add to more than 100%. There can be rounding errors in calculations where you get 99.9 or 999 or 100.001. But I don't worry, but that's a mathematical issue. Okay. So we have, if you look, I don't know if you're looking at the slides that I'm pulled up, but if we look at this, again, a certain very likely, 50-50, unlikely, or impossible. Again, a 5-value scale that we can look at. And there is a degree of likeliness or unlikely. Something that's very close to 100% probability is very likely. Something that's very close to 0% probability is very unlikely. And we use this as a way of analyzing the outcomes. Now, there is a complement, what we call the complement of an advanced. If we look at A and we calculate P of A, then the likelihood of A not occurring is what we call the complement. We call that P of not A. A with a bar over it is read not A. And if we add up P of A and P of not A, 100%. Because what we've done is say the probability of A is the event occurring divided by the number of repetitions. The probability of not A is A not occurring as in those repetitions. So it's if we look at the probabilities, if we want to express probability as a percentage, okay, the probability, okay, if we're flipping a coin, the probability of heads coming up is 50%. The probability of tails, which is not heads, is 50%. 1 minus 100 minus the percentage probability of the event. If something has a 75% probability of occurring, 3 out of 4, then it has a 25% of probability of not occurring. So P of A plus P of not A equals 1, or in percentage terms, 100%. Probabilities can be expressed either as a decimal or as a percentage. Remember, percentage is just decimal multiplied by 100. Okay. So we can express it either way. Mostly we talk about it in terms, statisticians prefer to use decimals, but most of us, when we talk about probabilities, we talk in percentage. Same thing. Remember that. So, all right. Okay. So we have also an issue. We talk about rounding off. We can either give an exact fraction. Okay, we did this experiment 10 times, and 6 times this was the result. So 6 out of 10 is the probability. We can also express that as a decimal, 0.6 as the probability, or 60% as a percentage. If it's not a nice even fraction, say it's 2/3 or maybe 7/22, or something like that, it's better to give a decimal. It gives us a better idea of the true probability. Okay, so you'll see both. We can express these as decimals. We can express them as fractions. We can express them as percentages. Okay, odds. Remember, I said that the odds, when in horse racing, the bookies give you odds, 3-2, 4-1. What does that mean? That means that what they have done is calculated the ratio of the probability of A, the outcome, this horse winning, compared, it's the ratio compared to the probability of not A, the horse losing. So if the odds are 4-1, that means that that means that they're out of 5 repetitions, 4 times that horse would be expected to win. That would make that a fairly safe bet. You're not going to make a whole lot of money, but you're not going to lose it all either. 1 to 4 means that there is basically a 1 chance out of 5. Because remember, A and not A, P of A and P of not A have to add up to 1, or whatever 100% is. So when we have the ratio, the odds are calculated basically as a fraction, which is P of A divided by P of not A. So if something's going to happen 1 time in 5, 1 to 5 are the odds of that happening. And it's 1 to 5 against. Because they're saying that out of those 6 repetitions, 5 times it's not going to happen. Okay, 1 to 5 against. So we use that. So we have the we'll talk about payoff odds, etc. That has to do with when we calculate odds, we're looking at the ratio of the probability of event A occurring and the probability of A not occurring. So P of A versus P of not A. Where does it? And that's where this comes in. This is the basis for all gambling, whether it's horse racing or craps tables at the casinos in Blackhawk or anything else.
You just count cards.
Hmm?
You could just count cards.
And really good card players do. And so the casinos have rigged their thing. If you go to play blackjack, I mean, I used to play blackjack a lot, not for money. We just played with friends, penny ante jackpot, blackjack. Yeah, if you count cards, you can often win. If you are better at counting cards, you can win. So the casinos now will put about 6 decks together, thus messing up the odds totally, but they'll only go through half of the stack before they reshuffle or replace the cards.
That's true.
Yeah.
Because I don't know, my friend said he was just in China and using my account.
Then it was unusual because the casinos have been doing this for years. Vegas has done it for years. If you go to Vegas and you look at a blackjack table, you'll see a stack of cards this tall. That's obviously not 1 deck. It's about 6. And they'll only go through half the deck. Because if you are counting cards, knowing now that there are 6 decks and therefore 24 aces, 24 of everything, right? You can, if you have that ability to track, you can increase your odds, but your odds aren't that good. So you can do it. That's why they only go through half the deck. And then they often replace the decks because people, deck cards get worn.
Oh, never mind. So
Pardon?
probability. I was like, but then wouldn't that mean that it's right back at the top? But I was like, well,
Right, it's all random. Yeah, and once you shuffle them up, and they use shuffling machines as well, a lot of times. So the issue is that we can do this. Now there is something called the rare event rule. The rare event rule yeah. Nate was talking to your computer a little while ago. At any rate, if we again look at a situation and understand what the probabilities are likely to be, okay? What is again we use this a lot for calculating probabilities. My weather app on my phone yesterday had some funny results. they were telling me that there was a 62% chance of 4 to 8 inches of snow. There was a 0% chance of 8 to 12 inches of snow, and a 1% chance of more than 12. I can't quite figure out how there was no chance of anything in between 8 and 12. That did not make sense to me. Okay. So again, looking at these things, you look at them, I just laughed at that and I thought, yeah, I'll mention that one. But the rare event rule says that if that given your set of assumptions, and this is what you have to understand from statistics, what are the assumptions being made? Okay, given your set of assumptions, if something is a very unlikely event, and then we see the thing occur, then we have to reevaluate our assumptions because it occurred, right? When something occurs, it has a 100% probability at that event. So if we are looking at our assumption set and we see something that our assumption set would say is very, very unlikely to occur, we go back and examine it. Maybe our assumption set is correct and it was just a very outside the outlier event, and maybe not. Maybe our assumptions are wrong. Okay. So we have to look at our assumption set as well. And assumptions are really important to look at. Okay. Okay. Let's look at another set of examples, and that is the addition rule, where we have multiple potential outcomes. And here's where rolling a die is a good example. Where we have multiple potential outcomes, such as we roll a die, we know that there can be 6 results. We can actually calculate what is the chance that we'll either get a 2 or a 3. Note that I said or. In this case, or is exclusive, that it is 2 or 3. It can't be both 2 and 3. There are places where where it can be and, but in this case, we've got 2 or 3. So that's additive. So we have a 1/6 chance of a 2. We have a 1/6 chance of a 3. We have a 2/6 or 1/3 chance that it's a 2 or a 3. Okay. Make sense? Okay. Okay, so we talked about simple events. We have compound events. Compound events occur in the case of we're looking, and this is definitional. Obviously, this is what we're looking at. Compound events are events where either one or both can occur. Now, the rolling of a die, we can have compound events. Okay, we can calculate a probability of a compound event, meaning 2 or 3 different potential outcomes. Obviously, it can't be both because it can only have one. The thing we want to be sure is that when we are doing our work, we look at the total number of ways that one event can occur and the total number of ways that a second event can occur. It has to be done such that we don't double count. And we'll get to some of those later. So basically you just add up the probabilities. Okay. what we want to do is, if we can look at this as, remember what a Venn diagram is? Venn diagram is two circles overlap, okay? Or they don't have to overlap. Separate events that can't simultaneously occur. There's no overlap in the Venn diagram. Separate events that under some circumstances can occur at the same time are in the common area of both. So we can have what we want to do is we can have mutually exclusive results. Rolling a die is, and getting a 2 or a 3 is mutually exclusive, because you can't get a 2 and a 3. However, if you roll 2 dice, you can get a 2 and a 3. Okay? And you can get it 2 different ways. Either if you rolled them separately, so that you know which die is which, then one can be 2 and the other 3, or it can be reversed, 3 and 2, but it gives you a 2 and a 3. So there are ways of doing that. We say that these are mutually exclusive or disjoint if they cannot occur at the same time. If they can, then we have to be sure that we don't make the mistake of counting. It depends on how we do it. Okay, we want to be sure that we don't count events at the same time. So the lots of ways. Again, if we are looking at trying to figure the probability of an event occurring repeatedly, then we're multiplying by each of the probabilities. If we're multiplying, if we're looking at a different set of results, we can look at doing combinations. I'm looking now at slide number 37 in the PowerPoint. We can make trees, okay, and we can come up with combinations. Now, when we're looking, this particular one has to do with basically test taking. As you know, test taking, if you can't figure out the answer, the question is it worthwhile to guess? Okay, let's just say you have 10 true false questions. And you are and you know the answers for sure to 9 of them. But you look at the 10th one and you say, I don't know. That's right. You can either not answer it and get a 0, or as long as there's no penalty for incorrect answers, which is one of the things that they often do on tests, as long as to prevent guessing, as long as there's no penalty for an incorrect answer, you have a 50-50 chance of getting the last one correct. So you're looking at taking at a 50% probability, just randomly choose one. So you flip a coin. True is heads, false is tails. Flip a coin, it comes up tails. You're right, false. You still have a 50-50 chance of getting that correct. You have 50-50 chance. Yeah, you can do eeny, meeny, miny, mo if you want. I don't care. But the issue is that you have a 50% chance of getting 100 instead of a 90. Is that worth it? Yes, it's always worth it. As long. Pardon? Well, yeah. I mean, that's different. I don't want to get into that. I mean, that is something. In that case, in true false, you have a 50% chance of gaining and a 50% chance of losing. when you make a guess. They don't. Yeah. There's no way to know if you've guessed. I mean, unless you have. And then obviously your answer would be at best guess. How do you know this? You don't. Yeah, because you're not. So, but if we look at it, say we have 4 choices. 1 out of 4. But if you can eliminate choices, let's just say you look at them and you can say, okay, well, choices B and C are obviously incorrect. And there's lots of those you can do. So now you've come down to a choice of just 2, and your odds of getting the right answer have gone up to 50%. Now, if you're penalized for wrong answers, you have to rethink that. But still, when you're penalized for wrong answers, a random guess of the 4. So usually what happens is so if you can eliminate, increase your odds of it. Okay. You've increased the chances of getting it. So this is why I tell people, if you don't know the answer, don't guess. For multiple choice, don't really guess. Think about it. See if you can improve the likelihood of getting it right by eliminating some of the choices. I'm not saying don't guess at all. I'm saying don't just randomly pick one. I don't want to think about it. Good thing, and pick out an answer. See if you can eliminate the choices. Sometimes you can do it. And when you have things like matching, I've always suggested that you can have matching on some of those tests. If you have matching, I've always suggested people go through and do the ones they know. And then you have a better chance of getting more points. So again, it's a case of looking at the likelihood of getting the right answer. Are we late again? Of course we are. I'm sorry. Please don't let me go past the times. I mean, I don't necessarily watch the clock. That's part of the problem. I'm sorry. Yeah, I understand. I hear you. I hear you. We're not going there.
Yeah, I hear you. Just
yeah, I know. And then,
Yeah, buddy.
I know you like that. That's not what we're doing. But I would like to go ahead and take some of the because we do have a lot of questions. Okay, so let's look at on page 148. Let's look at number 13 and ask ourselves, from our understanding of ways of expressing probabilities, which of these cannot be probabilities? So we're looking at number 13. So we've got 3 to 1. Is that a probability? Yeah, it is. It is. Because that's a calculation of odds. All right. What about 2 out of 5? 2 over 5. Right. 40%. Okay. What about 5 over 2? No. No. Because remember, the probability is the number of times that a result can happen out of the number of tries. And 5/2 would indicate that something happened 5 times in 2 tries. All right? Right. What about minus 0.05 or 0.5? How can a probability be negative? No. Probabilities are always positive numbers. Right. 0.5? Yeah, that's a probability. Yeah. How about 123 over 321? Yeah. 123 times out of 321 tries. So it's going to be a probability of a bit over a third. What about 321 over 123? Yeah. And then 0 and 1, are they probabilities? Yes, they are. Well, it means something can't happen. If it has a 0 probability, it cannot occur. Okay. All right, so if we look, no, that's 200%. That's 200%. So that's not possible. Okay. You can't get above 100%. And 100% is certain. And it's not additive. It can't be 100% on each of 2 days. So, right, 200%, no. Oh, they did? Well, they weren't supposed to. Ah, no hints. Okay. Yeah. Could be. Okay. So understanding that. All right. So let's look at okay, let's look at the number 9. Okay, in this particular one, we're supposed to express the indicated degree of likelihood as a probability between 0 and 1. Okay. So number 9, when rolling a single die at the Venetian Casino in Las Vegas, there are 6 chances in 36 that the outcome is a 7. This is a 0 probability. We're rolling a single die. You can't have a 7. Yeah. Yeah, this one says when rolling a single die. Now, does yours say something different? We're looking at number 9. 2 dice. Well, that's interesting because my version here has a typo. Well, there are 6 chances of rolling. Okay, change that to pair of dice. Yeah. Okay. Because the answer is a single die, you can't roll a 7. Right? So we're looking at there are 6 chances in 36 that the outcome is a 7, right? So let's take a look at that. You could different printing, and someone caught the typo in one of them, and they reprinted. So this is a different printing of the same text. So probably yours, Richard, is the later printing.
Yeah,
caught
I
it.
did that too as well.
You do?
Yeah.
Okay, so it's probably a later printing. So somebody caught that mistake. This book is remarkably free of errors. So there was a lot of, it should be a pair of dice or two dice. Okay. Okay, let's look at that. 7 can be composed of 6 plus 1, 4 plus or 2 plus 5, and 3 plus 4. Right? So that's 6 chances. All right. So 6 out of 36 is 1/6. 6 over 36 is a fraction of 1/6. Right. So there is, if you're playing dice, you have a 1 in 6 chance of rolling a pair of dice, a 1 in 6 chance of rolling a 7. 7 is considered an automatic winner on the first roll at the craps table. It's a killer on the second roll. Okay. So how many ways can you get a 6? Well, you can't have 6 and 0. So you can have 5 and 1. You can have 4 and 2. And 3 and 3. So that's 5 chances out of 36. So 5/36. So the chance of rolling a 6 with a pair of dice is actually a little less than the chance of rolling a 7. So when you're playing craps, if you were going to bet on a single outcome, you would bet on the 7. That's your highest probability. Every other possibility is a lower probability. For instance, a 2 with 2 dice requires 1 and 1. There's 1 chance in 36. How do we know there are 36 total? Because there are 6 sides to each dice. 6 times 6 is 36. Okay. Nate, you have a question? Okay. So when we're doing this, so this likelihood is on the unlikely end. It's not 50-50. So if we look at that vertical scale going from a definite event to no event, with the middle being 50-50, every single outcome is less than 50-50, significantly less than 50-50. The most likely outcome is a 7, and only 1 in 6 chance. That's why the craps table is yeah, well, yeah, it's crap, but that's why it's a risky way to play the game, except if you play a different set of odds. It can. It's harder. It can. Depends on the casino. But on the craps table, you have several choices. You can bet on a specific outcome. If you get lucky, you get a bigger payment. Or you can bet that when you can wait until a person rolls, so say they roll a 5 with their 2 dice. The chances of rolling a 5, you can get a 5 as a 1 in 4 or a 2 and a 3. There's 4 chances out of 36. Okay. So the problem is when you roll again. I mean, the issue is you want to roll and you duplicate the first roll, right? So you roll again. The chances are higher that you're going to roll a 7. 7 is craps at that point because it loses your bet. So the probability of losing goes up. Or you can bet on even or odd, right? Now, chances are pretty good when you roll 2 dice. You can calculate the odds of even odd. But it's going to be a cheaper payout. But it's a more likely event. Right? Gambling, playing dice is not a good idea. let's take a look at, there is, if we look on, let's take a look here.
Give a job. Awesome. Good for you, bro. I'm proud.
Great. Congratulations. Let's look at number 21 on page 149. The 110th Congress of the United States included 84 male senators and 16 female senators. Okay. If one of these senators is randomly selected, what is the probability that it's a woman? Okay. So if we just randomly select, say we give each of them a number, we have no idea what the number is, and we just choose a number. 16 out of 100 are female. So we have a chance of 16 out of 100, which is, can be reduced down to, 4 out of 25, 16%. So we have a 16% probability of selecting a female senator. $84 male and 16 female. So it's 100 senators. Okay. So we have, and that's a fixed number because there are 2 senators per state. As long as we only have 50 states, we're going to have 100 senators. So 16% of them in this Congress were female. So we have a 16% chance, or a 4 in 25 chance of selecting Now, does this probability agree with a claim that men and women have the same chance of being selected or elected as senators? It has nothing to do with it. This can't be used as support for a claim of any sort, because the data are at a point in time, they're cross-sectional data, one point in time. Has nothing to do with the election cycle. Okay, let's look at number 23 and see how, go ahead, Richard. They can still be elected, but there's nothing that says that they have an equal chance of being elected. It has nothing to do with the election process. Just saying that, if 50% of the senators were women, then that might support that statement. Okay, let's take a look down at number 23, called Struck by Lightning. In a recent year, 281 of the 290,789,000 people in the United States were struck by lightning. That many people were struck in 1 year. Nope. These are the data. So, yeah. So we can estimate that probability by simply dividing 281 by 290,789,000. So roughly 1 in a million chance of being struck by lightning. Yeah, not if you're the one struck. Yeah. So,
a better chance of being struck by lightning.
Okay, now let's go back and analyze the next question. Is a golfer reasoning correctly if they're caught out in a thunderstorm, and do not seek shelter from lightning during a storm because the probability of being struck is so small. Okay, when are you likely to be struck by lightning? No, when you're out in a lightning storm, if you're out in a thunderstorm. Okay, how much of the time do we have thunderstorms in any one area of the country? They're not very often. Well, or North Carolina, but lightning is not thunderstorms are not the issue. I mean, the issue is when we look at a number like 281 out of, call it 300 million, that's an aggregate of people at all times. Your probability of being struck if you're out in a lightning storm is much higher. And if you're carrying something that can be a conduit, it's even higher. I can remember many, many years ago, the college I went to down in New Mexico operated an atmospheric physics lab at about 11,000 feet in the mountains in New Mexico. And we used to go up there in the summer quite a bit. You know, when a thunderstorm was coming, they'd call us in because the chances of being struck at that altitude were significant. And I can remember being there and not able to get inside, and all of a sudden feeling the hairs on the back of my neck stand out. And I hit the ground and I rolled downhill. And lightning struck probably not 10 feet from where I'd been.
Really?
Yep. Yeah. Oh man, I felt good. I felt good about having had the sense to get down, because had I not been rolling down, the chances of it hitting me as a person standing in the open at that altitude would have been very much higher. But I went downhill rolling, and I took some lumps and got beaten up, but I also did not get blown away. Yeah, jumped. It jumps. No, not for sure, but the chance, there's a lot of energy, and the chances of you having some very adverse events up to and including death are very much greater. Yeah, you'll be unhappy. Okay. Well, yeah, you have to look at it that way. You have to, again, look at the data. 281 sounds like a lot of people. Out of 300 million, it's not a lot of people. But you know, being struck by lightning requires that you be out in a lightning storm. And most of us are not outside in lightning storms. You know, a lot of us, you know, we're driving our cars or whatever. That's not the same, because we have a cage around us. We're not likely to be struck. Tires are rubber, and so theoretically, you know, they will not provide as much of a conduit, although lightning can strike cars. They will not provide as much of a conduit for the energy. But again, looking at what are these data and interpreting it. This person, a golfer staying out on the golf course because they think, well, I mean, there's only a 1 in a million chance. But yeah, but what are the chances of being struck if you're out in a golf course? What is a golf course? A golf course is an open area. What are you doing? You're standing up. You're a conduit to the ground. So you've increased the probability of being zapped. Will you? Well, again, the answer to that is maybe. But you're more likely. Okay. All right. Is it that time? Oh, it is, isn't it? Yeah, let's take our last break, because I want to get into a couple of other things as well.
So when do you get to start there?
Honestly, don't know if I should tell you.
Why?
No, it's,
Why would you not tell
March
me?
5th.
I'm gonna go tell everyone.
And what are you gonna be doing?
I think
No way. No. That's not what you went to school for.
I know, right?
You went to school for a BS.
I know that.
Oh. I'll see a BS your way into
Yes.
IT.
Later on today. To be honest. Yeah. Usually don't know the answer to that. If we could use no. I did not go to that because the guy who answered was David Kelly. He said, absolutely not. I need to go. Because that's, yeah, why did we buy? Why are we spending all this money? That's my question. So, I'm going to our thinking about what our policy. But I think that's the rather. Yeah, it's not how we. But I was kind of shocked by it. Because I started putting it.
I mean, it's pretty. Yeah. I feel like it's easy. As soon as like you hit 3, it was like you're talking like quadrant. Yeah, and I feel like I would be able to at least use this maybe some way in my field opposed to.
Well, if you want to.
Yeah.
Yeah, really nice. If you're opening, it's basically like your business. Which I'm not.
Well, I think that's reasonable. If we can't use it, then what's to stop us from using the dollars? I was stunned by, and I heard the emotion in his voice, which is what it said. And I said, I think that was electricity, you know, it sounds like it's- yeah, that would make somebody. It was pretty, yeah, we just had a project.
Yeah. So it's gotta be something more like artificial. I've interested countries.
Yeah, well, I just want some, I don't want to know. Not supposed to,
Because
well,
you know that comes with those pieces. Well, you have another class this month?
Yeah.
Yes,
I don't know. Yeah.
nasty habit of being cold. Last couple of days. Oh. Yeah. I don't think the temperature on our back porch yesterday got above 10 degrees. When I got up in the morning, it was 0. And I don't think it got above 10 all day. 0 most of the day. And yeah, I was glad I had my pipes drained for my outside spigots.
Yeah, when you get to work and everything is, they're nice batteries, but and it's cold is strange.
Yeah, it does. Okay. Okay, there's a couple of other things. I'd like to talk about. And that is counting. You're going to see a problem. You're going to see a couple of other things. Let's look at. Remember, we said that the probability of A has a counterpart, a complement called the probability of not A. But there is a special sort of case. The probability of we can estimate the probability of at least one occurrence, or at least one outcome. Okay. The probability that the complement of that one outcome, the complement of at least one is none. Okay. At least one, the complement of that is no outcome at all. So if we're looking at at a probability question, the probability of none, the probability at least one of something happening is 1 minus the probability of none of them happening. Okay, it's easier to see sometimes how many cases none can occur, okay, versus figuring out how many times at least one thing can occur. Okay. So that's another one to keep in mind. Always. The complement is the likely that it's the complement of an event is the probability that it won't occur. 70% that it won't. Yes, that's the complement. Okay. The let's go into another set of concepts, which is going to be counting. Okay. There's a couple of fundamental rules in counting, and counting here really is. I want to get away from the 1, 2, 3 issue, but we want to calculate the number of possible outcomes in situations. Okay, so if there are a sequence of 2 events, okay, the possibility depends on the actual likelihood here, the number of ways that one event can happen and the number of ways that another event can happen. They don't necessarily have to happen in the same number of ways. All right. So the probability of them occurring together, or the number of possible ways that the events can occur together, are a multiplication of that. Okay. As an example, there are, if we're looking at identity theft, the issue is people stealing identity theft. One of the most common ways is to find somebody's social security number. One of the excuses used in a legal course was that somebody hadn't stolen their identity. They had simply guessed what their social security number was. Yeah, well, yeah, they still used it, which is a crime, but they hadn't stolen it. They'd simply guessed it. So they weren't guilty of stealing it. How that was going to help them, I don't know. But anyway, but what's a social security number composed of? It's composed of 9 digits, right? Each digit, if you look at between 0 and 9, okay, because there's no digit 10, right? That's a double digit. So there are 10 possible numbers that can be in that first number, another 10 possible numbers in the second number. So we've got 9 of these, and in each case there are 10 possibilities. So we have 10 multiplied by 10 multiplied by 10 multiplied by 10, 9 times. That's, if you remember from your algebra, that's 10 to the 9th, or 1 billion. So the chances of a person guessing a social security number for someone are 1 in a billion. Okay. Now, what is the chance that if you just randomly took 9 digits and strung them together, that you'd get somebody's social security number? Well, it's, if you just took somebody's, not a specific individual's, but just a valid social security number. Well, let's do that. Let's look at it. How many there are, in terms of 9-digit social security numbers, there are 1 billion possibilities, right?
At least.
No, There's one. That's it. That's it. Just 1 billion possibilities. There can be 10 choices for the first number, 10 for the second, all the way out, and it's only 9 digits long. So that's 10 times 10, 10 multiplied together by 9 times. You remember from your algebra, that's 10 to the 9th possibilities. So that's 1 billion possible numbers. There's 300 million in rough numbers, Americans. So that means that you have about a 1/3 chance of getting a correct Social Security number. Now, of course, Social Security numbers theoretically are retired when we die. It still leaves a lot, but but it does make you ask yourself what happens after we reach 1 billion issued numbers.
We're already at 300 million.
And that's living people today, but many of the original recipients of Social Security numbers from 1935, 36 are gone. You have about a 1 in 3 chance of getting somebody alive today. You might find that it's somebody who's passed away. Might be a retired member. Oh no, it's still illegal.
Well, I mean, you didn't.
Yeah, still. But anyway, nonetheless, there is the probability. That's how we calculate that. Okay. We can do that. But let's take a look. That's one example. So we have, it's extremely unlikely he could, by chance, pick your number. Okay. By just doing it one time. They might generate 100,000 numbers and try using them until they found one that worked. That's a different set of probabilities. The other example they give, and I want to go into this because we're going to get into something called the factorial rule. Do you remember what factorial means from algebra? Yeah. Not factoring. Factorial for a number. Factorial is of a number written as, we'll use n as the number with an exclamation point behind it. That means n factorial. That means if we just take each sequence, each number in sequence that adds up to that and multiply it together. So that 7 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7. Right? This tells us basically the number of ways different the number of ways a number that a specific number of things can be arranged. Practical example. Before a football game, the players on the team come out and line up. How many different ways can they line up? And let's take a look at how that works. And let's just say the 11
members are going to be the starting team on the field. Let's not do the full 30 odd members of the entire team. But let's just take the 11 members who will be the starting players on a team. So we have 11 players. Okay, so if we line them up, okay, I've got 11 stars here. Okay, we have 11 possible players that can be number one on that line. Now we've taken one out. So the next one can be one of 10 players. And we've taken out another one, so the next one can be one of 9 players, etc. So we're reducing the number of choices. So remember I said that the number of ways that something can occur multiplied together gives us a sequence like that. So now we have 8, 7, 6, 5, 4, 3, 2, and then there really isn't but one choice for the last one. It's whoever's left, right? So now if we use that rule for counting of the number of ways that something can be arranged, multiplied by each of the other components, we've got 11 times 10 times 9 times 8. That is 11 factorial. Okay. So that's the basis for that number. What we're doing is we're saying there are 11 times 9 times 8, et cetera, ways that team can be lined up in a row random. Okay. Obviously, they don't do it. But if it were truly random, that would be how many possible combinations of players could be lined up. Okay. Now that's the universe. It doesn't mean that that's the way, that it's going to happen that way. And you can imagine if you take all 35 or 38 or whatever members and then throw in the coaches, if it were truly random, this is a huge variety. And that's the basis for that 1 billion number. Now, this factorial issue assumes that each time we take a player out. I mean, each time we put one up, we've taken a player out. With the Social Security numbers, we don't pull a number out. There's any of the digits can be anything from 0 to 9. Okay, so we don't pull anything out, right? So we have that. So what is the use of this? So we're going to get to that next because it does come in. And we're going to relate it to a problem that they have okay, let's go back and look at a problem on page, starting off on page 185. Okay, let's assume that we have someone who's going to go to who wants to do surveys in state capitals, but can only visit 4 state capitals. And let's put no restrictions on which capitals they can be. Okay, so we've got 50 choices for state capital number 1. And we want to know what order we can possibly arrange. What are our choices? Now, if we choose our first one, let's just say we decide that we want to start in Denver. So we've chosen Denver. We chose Denver. That's but there were 50 possible choices. Now, having chosen Denver, we now have 49 possible choices for state capital number 2. So let's assume next that we choose Raleigh, North Carolina. So now we have 48 for state capital number 3. Let's assume we choose Sacramento, California. Now we have 47 left for the 4th one. Okay. So that means that in the absence of any other decision, we have 5,527,200 choices. 50 times 49 times 48 times 47. Okay. Now, if we look at this, let's just go and put this on the board, and I'll show you. There's a little formula that we can actually look at. We started off with if we were to want to visit all 50 states, we were to visit all 50 states, then it would be 50 times 49 times 48 times 47 times 46 times 45. Okay, all the way down to times 2 times 1. Okay. But we only want 4. So we picked our 4. So that 5 million, whatever number, 557,200, can be expressed in a slightly different way, in a more general way. It's the same. We have eliminated everything below from 46 down. So that part of the factorial this is 50 factorial. We start with all 50 states. We've eliminated 46 factorial, so we divide this now by 46 factorial. What does that do? Well, if we have something that is a series of numbers and we want to actually calculate probabilities and choices, then we can simply divide by the factorial that is the factorial of the number that is below our last choice. So this may look complicated, but if we look at it in a slightly different way, which is what we're going to have here. I'm gonna put it up here as a formula. If we have n different items available, remember we have n different choices, right, available to us. Okay. And we want to select some number. So we have n choices. We want to select r choices. And in this case, put a caveat on it, without replacement, meaning when we did the social security number, okay, the first number maybe we chose was 5. That does not mean that 5 has disappeared from the choices for the next 8 numbers. So we've replaced it. In the case of the 50 states, when we took out Denver, Denver is not going to be revisited. We only need to survey it once. So now we've removed that choice, and we haven't added a theoretical 51st state to it. Right? So this is no replacement. Okay. So we have those many choices. And we want to consider rearrangements. Okay. We consider rearrangements of the same item to be different sequences. In other words, it doesn't matter if it's Denver first. We are looking at it matters that Denver is first, and then Raleigh, and then Sacramento. Raleigh, Denver, Sacramento would be a different set of choices. So we consider rearrangements to be different. Okay. So the number of permutations or sequences, all these permutations. Okay. We'll call that P. But we have to define P in a different way. P of N choices and R selections. Okay. Is defined as N factorial over N minus R factorial. So if we look at this, we had 50 choices. Okay. We chose 4. So R is 4. So in this case, this would be 50 P4. That tells us that we had 50 choices at the beginning. We're only going to take 4 of them. All right. So those 4, that means that in this case, N factorial is 50 factorial. N minus R is 50 minus 4, or 46 factorial. So if we are given, if we are told to use a formula to calculate something, then we want to use, you're generally going to be told what to use. Okay, told how to do this. There is another variation on this topic. Okay, so as another example, where we have the arrangements as being all the same. So Denver, Raleigh, Sacramento is the same thing as Raleigh, Denver, Sacramento. Okay. So we use a slightly different formula because we have to take into account that we are reducing the number of choices when R, okay, for our second choice, if it didn't matter, if all of these were considered equal, our second choice would be R minus 1. So we've actually reduced those choices. So we have, now if we have, this assumes if the order matters, in other words, ABC is different than BCA, right? We use this formula. if the order doesn't matter, in other words, if ABC and BCA are the same, then we have a slightly, we use the symbol C, and we've got NR equals n factorial over n minus r factorial times r factorial, because we are reducing the number of choices we have now. We have now taken out our next round of choices if it doesn't matter. Okay. So in this case, if it didn't matter which direction, which order we were visiting this particular problem, it would be 50C4 equals 50 factorial divided by 46 factorial times 4 factorial. Okay. Now, why do we set it up this way? If we notice this, when we're doing our math, we can do this the hard way. We can calculate 50 factorial. In fact, some of your calculators allow you to do that. But there's a simple mathematical way of doing it, which of course is 50 factorial is going to be 50 times 49 times 48 times 47 times 46 factorial. Right, 46 times 45 times 44. So 50 factorial divided by 46 factorial equals 50 times 49 times 48 times 47. Multiply, pardon? 47. Yeah, not 74. Thank you. Okay. So that's an easy calculation. Now you only have 4 numbers to multiply. This other formula adds a different kind of a second calculation. Okay. 46 factorial times 4 factorial now becomes 50 times 49 times 48 times 47 divided by 4 factorial. 4 times 3, 12 times 2, 24. Okay. So this becomes 4 factorial now is 24. And we can simply divide 24 into 48 and get a 2. So that changes the calculation. So what I'm urging you is to do math the lazy way. I believe in being lazy, I use the word lazy kind of advisedly. It's much more efficient to do it this way. You don't have to waste a lot of time. But remember that you can just divide these things out. These look complicated until you put them together and look at it. Oh yeah, that's easy. Now we can knock that out. So here we have something that is 1/24, roughly 4% of the original 5 million, etc. We've taken a big chunk of choices out by saying the actual routing, the order of visiting these capitals doesn't count. Okay, makes sense? So instead of 5 million, there's more like 20,000 choices, potential choices that could be made. Right? And this applies to some problems that you'll have in the homework. Now, homework. Yeah, we're getting close to the end of this class. So what I want to do your chapter 4 has a number of questions. What I want you to do is remember that we can look at, I talked about the possibility of different probabilities, either or is exclusive. It's either A or B. But what about something that can be a couple of choices? Let's just say choices for breakfast over at McDonald's. Okay. There are, let's just limit it a little bit to sausage McMuffin, sausage biscuit, pardon? And a McGriddle, okay? Okay. Okay. So what if you wanted to know the number of people that wanted sausage McMuffin or McGriddle? Okay. That can be or in this case is meaning it can be either one. So what you want to do is be careful when you look at these problems that you ask yourself, are we being exclusive or are we being inclusive? Okay. If you go into a Chinese restaurant, you've got lots of choices on the menu, right? And if you've got a group of people, you're probably going to get several choices. What are your possibilities? What's the possibility that someone will order, chow mein in the party and the other General Tso's chicken? Okay. That's an and. So we're looking at, and we're combining those two. We're looking, don't forget that there is an exclusive and an inclusive way of looking at these things. So look at your problems carefully from that standpoint. If you have trouble, you ready for that? Great. Super. Do you have anything else? Anybody else have anything to say? Okay. Chapter 3 homework. I will tomorrow, but you can leave something for me. That's not a problem. Roberta can take it, or you can leave it with, any of the people. They'll get it back. They'll leave it in my mail slot. I usually check the mail slot each day.
Unless you come in great paper beforehand.
No, I won't. You can also scan it in if you want. So anyway, what I wanted to do quickly, just take a quick look and see. Okay, remember a complement to an event is the non-event. And a complement to at least one is none. Okay. When you're working on these when you're working on these problems, you're going to have several. You're going to have a couple. You're going to this permutation and combination thing appears at the end of the homework 4. And what I will do before you all leave, I'll just go ahead and make copies of this. But be very careful about reading the problems. Your key is, does the order matter when you're doing these permutation and combinations? Does the order matter or not?
And if it does, then you use the NPR formula. If the order doesn't matter, you use the combination formula, the NCR. Okay. Questions? Read through the chapter, look at the examples. Randy, you look like you have a question. Permutations where where the order matters, where ABC is different from CBA. Okay, where it doesn't. No difference in ABC and CBA. It doesn't matter. There's some of both on this page. So think about the problem. Take your time on that. Now, the homework from last week assignment, the 120-point assignment, there's a combination of essay and problems. I forgot to pull some problems out. If you work on the problem, and then I modified the assignment for those of you who haven't looked at it. I modified the assignment. If you do some of the extra problems, I'll give extra credit.
Was that for this week or
Last week's. So I will give extra credit if you do some of the extra problems, because we didn't cover that material in class, at least not at all adequately. And so, try them. You have nothing to lose. You don't lose anything by getting them wrong. And we'll have to see from the rest of it. But don't forget the essay part, please. So I'll be right back. I'm going to go ahead and copy this and bring you guys copies.
are you waiting for No. Good. Is it fun? It's on Netflix. You got more than he's gonna talk to me. Nice thought. Which is only asked to hang out with me. Why? Because she has a friend. Well, there's these girls, and like, well, it's basically one of my friends I know in elementary school, and I moved and I started doing my own thing, and like, she always hits me up when she's coming down to Colorado. Okay, then she's like, "Well, can I stay there?" I'm like, "Sure." Then she finds one of her other friends who let her stay there, and she blows me off, and I'm just like, "You're pissing me off." I'm just like, if you don't want to stay here, don't use me as a last resort. Okay, we're supposed to be friends, so like, if I'm gonna start saying yes to all your fucking friends staying at my house, and you can go fuck off. Like, don't come at me like that. I just hate how people are so fake nowadays. You can't, like, you know. It is. It is about manipulation and power. 100 people. No.
I mean, I'm not much older, but my
It is.
a little bit older than you.
Because they had to be
Sorry.
kidding, they had to be co-responsible.
Got caught in a conversation.
Thank you.
about-
Oh, lovely.
It's silliness that doesn't affect you. Don't worry about it. But yeah, have a good weekend, everyone, after a short week. Please, if you have questions, send them. And we'll have time on Monday to spend, we have to cover a couple of other topics. But we'll have time on Monday and Wednesday to spend on this, and then we'll, if we have to, we can, we'll see what happens with the time. That may have to be taken. Because we just, losing a day in a class like this is hard. And it's hard for you guys, it's hard for me. So have a good weekend. We'll see you on Monday morning.
All right,
And
take
April,
care.
please bring that stuff.